Welcome to this presentation on vegetated filter strips, prepared by Marty Wanyalista and presented through BMPFast. A vegetated filter strip is a recognized best management practice included in the applicant's handbook under Green Stormwater Infrastructure. These systems are typically found adjacent to impervious surfaces like highways and parking lots, and they are commonly applied in high water table areas where groundwater percolation is returned to a surface discharge. In this module, you will learn about vegetated filter strips, commonly referred to as VFS, including what they are, where they are used, and how to calculate their average annual effectiveness. We will walk through a definition of the vegetated filter strip and develop an understanding of how it functions as a stormwater management practice. The filter strip is one of 13 best management practices with wide acceptance in Florida, making it an important tool to understand. From there, you will learn how to navigate the analysis tool, enter data for an annual mass removal analysis, and interpret the output results. We will work through an example project together, and you will also learn how to save your data using the .bmpt file format. The vegetated filter strip, or VFS, is a constructed and maintained area of vegetation that is deliberately placed between a source of runoff pollution and a receiving water body. These pollution sources might include roads, parking lots, or agricultural fields, and the VFS serves as an intermediate zone that captures and treats that runoff before it reaches open water. The primary purpose of a VFS is to remove non-point source pollutants, particularly nutrients. Because of this treatment function, a VFS must include some form of media capable of actually removing those nutrients from the runoff. The treated discharge ultimately flows to a surface water body. One important design constraint is that when assessing the effectiveness of a VFS, it is typically treated as a standalone system. This means the area of the VFS itself plus the contributing drainage area must together equal the total catchment area. That relationship is essential for properly sizing and evaluating the system. It is also worth distinguishing a VFS from a vegetated buffer, because these two terms are sometimes confused. A vegetated buffer is a natural area that has not been subject to construction activities. A VFS, by contrast, is deliberately constructed and maintained, meaning it has been shaped by human activity. That distinction in origin and intent is what separates the two, even though both involve vegetation near a water body. To wrap up, let's look at some real-world example applications of vegetated filter strips. These systems are commonly applied in three main contexts: residential or housing developments, roadways, and parking lots. However, there are important siting limitations to keep in mind. The slope of the vegetated filter strip in the direction of flow must fall between 2 and 20%. A slope that is too flat won't move water effectively through the system, while a slope that is too steep can cause erosion and reduce treatment performance. Additionally, each filter strip requires a minimum width of 15 feet to function properly. The data and guidance used in these examples draw from a range of sources, including state environmental agencies from Texas, Ohio, and Washington, the EPA's NPDES Stormwater Best Management Practice Guidelines for Vegetated Filter Strips, and local research on hydraulic and nutrient removal performance, particularly for roadway runoff applications. One specific design approach for meeting total nitrogen and total phosphorus targets involves the use of a BAM mix within a vegetated filter strip configuration. The maximum width for which we have reliable performance data is 30 feet, and that boundary is important to respect when applying this design in practice. The efficiency data supporting this approach comes from published research by Mohammed Shokri, examining hydraulic and nutrient removal performance of vegetated filter strips using engineered infiltration media for treating roadway runoff. That work has helped establish both the runoff handling capacity and the absorption capacity applicable to Florida conditions, giving designers a solid foundation for their calculations. One important characteristic of most implementations is that they do not include an underdrain pipe. Instead, water percolates through the BAM mix and moves toward the adjacent ditch, ultimately discharging as surface water. Understanding that flow pathway matters when you are evaluating where the treated water ends up and how it connects to the broader drainage system. This project involves a 2-acre roadway located in the Tallahassee area that is part of a Basin Management Action Plan, or BMAP program. The goal is to calculate the average annual removal of total nitrogen and total phosphorus for a specific vegetated filter strip design, which we'll refer to as a VFS. The VFS has some specific design characteristics. It includes a 1-foot-deep biosorption activated media layer, known as BAM media, with a storage capacity of 0.38 inches per inch and a slope of 4%. The VFS can store 6.6 inches of runoff, and that storage value is used to back-calculate the curve number using the relationship storage equals 1,000 divided by the curve number minus 10. That gives us a curve number of 60. The site also has a directly connected impervious area, or DCIA, of 70%. Rather than using default event mean concentrations, this analysis uses user-defined EMCs pulled from an adjacent roadway, which gives us site-specific pollutant loading data to work with. The catchment area is made up of both the contributing roadway area and the VFS area combined. The roadway DCIA has a width of 60 feet, the VFS adds another 26 feet of width, and the total length is 1,013 feet. Multiplying 1,013 feet by 86 feet and dividing by 43,560 square feet per acre confirms the total area equals exactly 2.0 acres. This project was originally permitted as an environmental resource permit meeting performance standards of 55% TN removal and 80% TP removal. However, for BMAP compliance, we need to go further and calculate actual pounds removed per year. We'll be using the BMPFast software with the Vegetated Filter Strip module to generate those results. When entering the site and watershed data, the information you provide reflects the specific location and characteristics of your project site. One important assumption built into the Vegetative Filter Strip tool is that water does not infiltrate into the ground, which means there is no need to conduct a groundwater analysis as part of this process. It is also worth noting that the best management practice analysis is performed based on post-condition land use. This means you are looking at what the land use will look like after development or project completion, and those conditions are what get checked and verified against the inputs for your project. Now we enter the physical dimensions and media treatment data for the system. There are important constraints to keep in mind for each input field. For example, the slope must fall between 2 and 20%. If any of your values fall outside the accepted range, the recommendation is to use the limit value that the software allows. To illustrate this, if your vegetated filter strip width is 35 feet, you would enter 30 feet, since that is the upper limit. Keep in mind, though, that the minimum allowable width for a vegetated filter strip is 15 feet, so anything below that cannot be used. For the media residence time, this is calculated by taking the depth of the media and dividing it by the rate of infiltration. In this example, we have 12 inches of media depth and an infiltration rate of 5 inches per hour, which gives us a residence time of 2.4 hours. This tells us how long water is in contact with the treatment media, which directly influences how much pollutant removal occurs. Once all the data is entered, the software calculates and displays the pollutant removal in kilograms per year, giving you a clear picture of the treatment effectiveness of the system. Enter the configuration data, which includes the routing and BMP selection. Once that's complete, navigate to the summary section to enter the summary data. For this highway, the vegetated filter strip meets the percent removal required by the environmental resource permit. When calculating the BMAP credit, the total nitrogen comes out to 7.64 pounds per year, and the total phosphorus is 0.789 pounds per year. Make sure to save your project data before moving on. To wrap up, let's review what we covered in this presentation. We explored what a vegetated filter strip is and how it functions as a best management practice for removing pollutants from stormwater runoff. One of the key things to remember is that when working with a vegetated filter strip, the catchment area must equal the combined contributing area plus the VFS area itself. These systems use select media to reduce pollutant concentrations in runoff, and the discharge from the VFS ultimately enters the surface drainage system. We also walked through how to navigate BMPFast and enter the appropriate data to conduct an annual mass removal analysis, and we looked at how to interpret the results that the software generates. Through our example project, we saw the real-world value of BMPFast in the context of both Environmental Resource Permit, or ERP, programs and Basin Management Action Programs, known as BMAPs. Specifically, we verified that the pollutant removal percentages calculated by the software align with what is required for ERP compliance, and we identified what credit can be assigned toward a BMAP. Finally, remember to save your BMP analysis as a .bmpt file so that your work is preserved and ready for use in future permit applications. Thank you for watching. That brings us to the end of this module on vegetated filter strips. We've covered the foundational concepts behind how VFS systems work and walked through how to evaluate their effectiveness using BMPFast. If you feel you need to strengthen your understanding of any related topics, take some time to explore the other learning modules available to you, and when you're ready, you can apply to take the competency test. Just refer to the module called Self-Test for details. Thank you for watching.